Hello, welcome you all to the. Just a moment, I think I haven't shared my screen yet. Okay, hello, welcome you all to the third problem solving session for the NPTEL course titled Multirate Digital Signal Processing. Myself, Saurashis Chatterjee, a PhD scholar from IIT Kanpur. So let us start today's session. Today's session will solve the following problems. So let us move to our first problem. So the first problem says a sequence is given xn and the index of the zeroth entry is also mentioned in a box. So it is said that xn is downsampled by a factor of 3. So what should be the output? So let us first write down the sequence xn. I have deliberately removed the options so that when we derive the correct answer, we will get straight to the point. Okay, the zeroth entry is here, 1. Fine. It is said xn is downsampled by a factor of 3. Xn passes through this box which denotes downsampling by a factor of 3. We get the sequence yn. So according to the mathematical representation of downsampling, yn is denoted as x3n. That the intuition here is we are going to select one out of let me correct myself here, one of every 3 samples, and we will discard rest of them. So let me write the sequence xn again so that it is clear to us what the sequence yn is going to be. That zeroth indexing is very important, so I am highlighting it with a different color here. So while downsampling by 3, we are going to pick the 0th index 1. We say no to next to some samples, then pick 4 again, then again no to these two, we'll discard them, then 8, 7, discard these two again. So this results into the sequence yn being denoted as 1, 4, 7, 10. Why we choose these specific samples only? Because they correspond to indexes which is multiple of 3. This is 0th index, this is first index, this is second. 1 and 2 both are not multiples of 3, so we are going to discard them. This is third index, multiple of 3, so we are going to keep it. 5 and 6 are respectively 4th and 5th index, again not multiple of 3, we are not going to pick them. 7 is 6th index, so we are going to pick it. 8 and 9 again 7th and 8th index, not multiples of 3. And 10 again 9th index, so we are going to pick it. So our output is going to be yn, which is denoted by this sequence. Okay, let us move to second question. Again similar kind of question, almost similar to first one, just here there is a advanced operation being performed. So let me write down the sequence again. xn By the way, there is one point I have missed saying. We are going to ignore this sample also, because this correspond to -1 index, which is not again a multiple of 3, so we are going to discard this also. Sorry, I forgot to mention it. Okay, let us move to the second question. 7, 8, 9, 10. Okay, now this is again the 0th index, let me denote it. Now instead of downsampling xn, we are going to downsample yn, which is xn plus 1. So you basically obtain yn if you remember the lectures, we denote the advanced operation as z. We are going to get xn plus 1 as yn. Basically we are going to shift the sequence to the left by 1 index. Let us write it down to see what the sequence look like. I am putting it inside this third bracket because it denotes the 0th index now, because the entire sequence shift to left by 1 index. It is equivalent to 1 unit of advance. Now this yn is being downsampled by a factor of 3 to obtain, let us we denote the new sequence as x dash of n. So the mathematical representation again of x dash n in terms of yn is this. So we can write it this way also, as it x dash of n is equal to y of k for k is equal to 0, 3, 6, that is multiple of 3, and 0. Otherwise the principle remains same. We are going to pick one out of every 3 samples and discard the 2 samples whose index is not multiple of 3. So from this yn, let us try to write the new sequence x dash of n, which one we are going to pick and which one we are going to discard. So this corresponds to -1 index, so not a multiple of 3. By the way, it should be plus minus to be correct. We are going to discard this. We are going to pick the 0th index. This is first and second. We are going to ignore them. This is third index. We are going to pick it. These are again 4th and 5th index. We discard them. This is 6th index. We are going to pick it, and we are going to ignore the other two because this corresponds to 7th and 8th index. So your new sequence, your downsampled sequence x dash of n is given as this. This is the 0th index. So this is your output. Okay, let us move to question 3. Again similar kind of question but slightly tricky. Let us write down the sequence xn first. This is the sample correspond to 0th index. Now it is said that xn is upsampled by a factor of 4 to obtain yn, and then yn is downsampled by a factor of 2 to obtain zn. So there is a upsampling process first followed by a downsampling process, and the factors are different in both cases. So what is the output sequence zn? Okay. So let us first denote the operation by a block diagram so that overall picture kind of becomes clear to us. xn passes through a upsampling block with a factor of 4. We obtain yn, and this passes through a downsampler block, the downsampling factor of 2, and we obtain the output sequence zn. We are interested in zn. Before we proceed, let us write the principles. The first one is like that: upsampling by a factor of L introduces L minus 1 zeros between every two adjacent samples. And second principle which we are going to use, these two are very basic, very fundamental, but also at the same point of time very important: downsampling by a factor of M keeps one out of M samples and discards the rest. So first we are going to find the sequence of the upsampler block, that is yn, intermediate sequence, and then we will proceed to zn. So let me write down the expression of xn again. Here we are, so let me write down the mathematical representation of yn also. And basically x n by 4, because it is obtained by upsampling xn with a factor, upsampling factor of 4. So by this first principle, here we are upsampling by a factor of 4, so we are going to introduce L minus 1, that is 4 minus 1, which is 3 zeros between every two adjacent samples of xn. That is how we are going to get yn. So let us write yn. Yn will look like that: 3 zeros between 1 and 2, again 3 zeros between 2 and 3, and similarly for rest of the samples. Oh, sorry, I need to introduce one more zeros here. Okay, so this is our intermediate sequence yn, which we obtain by an upsampling process with upsampling factor of 4 of xn. By the way, this is the 0th index. It's pretty important when you do this all upsampling and downsampling process, which are time variant process. You must keep a very good look at your sample at 0th index, the position of it. It depends a lot. I mean, the process depends kind of entirely on it. So Now we'll try to find the mathematical expression of Zn. Zn is y of 2n. 2 is the downsampling factor. So by this principle, Zn is going to be something like that. Let us look at the principle again, that we are going to keep 1 out of m samples. M here is 2, so we are going to keep every 1 out of 2 samples, and we are going to remove the other one. It's kind of we are going to keep every other alternate sample. Let us see how it's done. So it's like that. We are going to keep the 0th index. Let me denote it with a different color. This one, going to ignore this one we are going to keep, this one we are going to ignore this. So basically we are going to keep all the even indices, samples at the even indices, and remove the samples which are at odd positions. So something like that. I am not showing for all these samples. I'm just writing the resulting sequence because it would be kind of messy. So Zn would look something like that. Oh, it ends at 8, sorry. So do you see some kind of similarity between xn and zn? You see, Zn is nothing but xn with the additional 0 introduced between every two adjacent samples. So by this principle, it kinds of, let me denote the 0th index here, kinds of look like that Zn is a upsampled version of xn, where the upsampling factor is 2, because you are introducing 1 zeros between every two samples, so it must be upsampling factor of 2. At least it looks like that. See, if we look at this block diagram, we also get that proof, because we can write this block diagram in this way. If we remove the notation of yn in between, we see we are obtaining Zn by performing upsampling with a upsampling factor 4 on xn, followed by a downsampler block with factor 2. So if we remember the lecture correctly, we can write this upsampling block with factor 4 as 2 times 2. And given there is no filtering, or that, these two are going to cancel each other. So the resultant system is like this. Only a upsampler block with factor 2 between xn and zn. Now you can see that this is this is, sorry, let me correct myself. This is in coherence with our observation. It seems as if the intermediate, we can replace this upsampler and downsampler block with different factors, as by upsampler block with upsampling factor of 2, which is coherent with our observation here, by the way. So instead of following this manual process, like first performing upsampling by factor of 4 and by downsampling 2, you can efficiently follow this route also, so that you need to perform only one upsampling operation, that also by a factor of 2, which is less computationally expensive, to find the output sequence Zn. Okay, with this we'll move to the fourth question, where again similar kind of question, but the order of upsampler and downsampler block are kind of reversed. So we'll see what kind of impact it is going to make. But let us first write down the sequence Xn. This is 0th index as usual. So it is said Xn is downsampled first by a factor of 3 to obtain Yn. So it's like that. Perform downsampling first to get Yn. You then pass this Yn through a upsampler block with a factor of 4 to obtain Zn. Let us see what's the observation for that. By the way, a small thing here. If the order of block is reversed here, do you think that this assumption still hold? I mean, if I put this downsampler block here and upsampler block here, do you think this is going to still hold? Let me write it down. What my question is. If order of blocks reversed, okay, let me not write down this, just explain to you in few seconds. See, if you put the downsampler block here, you are going to lose these odd index samples, and then when you upsample by a factor of 4, you are going to basically introduce zeros, but you lose this information to 4, 6, this odd index samples. So the impact is not going to be the same. So you should be very careful what is the order of upsampler and downsampler. That is why upsampling is generally preferred at first, to avoid any loss of information. We can see the kind of impact in the next question that we are going to encounter for here. So I will proceed little fast here. We will see the sequence yn is x of 3n. I am directly going to write the sequence here. It's like 0 first, then ignoring 1 and 2 we'll move to 3, then again ignoring 4 and 5 we'll move to 6, and that is it. Now when you perform upsampling, by a factor of 4, it basically means you are going to introduce 3 zeros between each adjacent samples. So we can see this is our resulting signal Zn. So let us try one thing here. What if we have this diagram instead of the earlier one? That is, we do upsampling first and then we perform downsampling. How is the sequence going to be different? Let us denote as y dash and z dash n. Xn remains the same input to both system. So let me write y dash n. By the way, this is the answer. This sequence is the answer for the original question. We are just trying a variant of it by exchanging the order of the blocks. Y dash of n is going to be nothing but 3 zeros inserted between each pair of samples, and our z dash n is going to pick every one out of 3 samples So you can see you are going to get the same sequence in the earlier case by exchanging the order of blocks, and this is going to happen, and this is only happening because Zn and Z-n are same, because 4 and 3, that is the downsampling and the upsampling factor, are relative prime. In other words, you can say Crow prime also. This is a very important observation. This gives you an idea that at what situation you can change the order of downsampler and upsampler blocks. So let us move to question 5, which says that continuous time signal xt cos 4000 pi t is being sampled at 8000 Hz to obtain xn. Xn is next downsampled by a factor of 2 to obtain yn. So what is the yn? So if I represent in terms of block diagram, it will look something like that. C to D, where the sampling period is this. You are getting xn here, which is next passed through a downsampler block to obtain yn with the downsampling factor 2. So let us make use of this fundamental continuous to discrete time representation, like the equivalence between them. X of nts, so x is cos 4000 pi t, we replace t with nts, where ts is the sampling period given by 1 over 8000. So it is 4000 pi nts. It is nothing but 4000 pi n over 8000, which is cos pi n by 2. Now you are performing downsampling operation, yn, the downsampling factor of 2, which is given as x of 2n. If you substitute the value here directly, you are going to obtain cos pi n by 2. N is replaced by 2n, so let me write 2n here, pi times 2n cos of pi n. Now this immediately matches with the third option, but before taking any option, you should check the other options also carefully, if there is any overlap or not between the options. If you move to the fourth option, it says that is the option that says that both 1 and 3 are correct. You know the 3 is correct, but you need to check whether this one is correct or not also. So cos pi n, you can see, you can write it as like this. It is 1 for n is equal to 0 to 4. Basically n is equal to even, cos pi n is 1, and it is going to be 0 for n is equal to 1, 3, 5. Basically odd. So can I combine these two results and write it as this? Because you see, when n is equal to even, minus 1 to the power n is going to be 1 anyway, and if it's odd, it's going to be minus, oh sorry, let me correct myself, I routed 0 here, so blunder, it should be minus 1. Okay, when they club these two results, n is equal to odd, this is anyway going to result in minus 1. So for this problem, for this problem, cos pi n and minus 1 to the power n are both correct answer. So option 4 should be the correct one. If you tick individually on this or this, it is not going to be correct. Okay, let us move to the sixth question. So you see, the block diagram is already drawn here. So this is our input sequence xn, which passes through a downsampler block with a downsampling factor of m, and then it passes through upsampling block with a factor of m to obtain the sequence y. Okay, so the seeing the options, it basically is concerned about the discrete time spectrum of y, output sequence yn. We need to represent the spectrum of yn in terms of xn. Fine. So I'm going to use a result from the lecture in case of downsampling. So it is like this, if you correctly remember. When xn passes through a downsampler block with a downsampling factor of m to obtain new sequence yn, then the spectrum of yn let us denote it in terms of z transform, because we can always move to z to omega by using the substitution z is equal to e to the power j omega. Z transform is basically DTFT performed on unit circle. So x z, that is the amplitude scaling 1 over m, there is a stretching of frequency domain, and there is a frequency shift part. All of them are important. Oh, by the way, here it is not xz, it should be yz. So you can see downsampling results into in spectrum terms in frequency domain amplitude scaling. This represent multiple copies of input spectrum this is stretching of frequency axis, and this represent the shift, the position of different inputs, the position of the same input spectrum, different shifted version. By the way, the Wm we denote, it is nothing but a to the power j 2 pi over m. Fine. So if I denote this intermediate sequence as x dash of n, which is obtained after downsampling xn by a factor of 2, and we denote the corresponding spectrum of x dash of n as x dash of z, we obtain this x dash of z is equal to 1 over 2 summation k is equal to 0 to 1 x z to the power half a to the power of, sorry, I need to remove the n here, very sorry. No. And a to the power minus j 2 pi k by m value is 2, put 2. So it is this. Okay, let me write it in an elaborate way so that there is no confusion. The power half a to the power minus j 2 pi k for k is equal to 0 minus j pi k, it results into for k is equal to 0 it's 1, for k is equal to 1 it is minus 1. And when we replace x is equal to a to the power j omega, we can write this as x a to the power j omega by 2 plus x e to the power minus j omega by 2. Now when you move from x dash of n to yn, the upsampling factor of m, the relation between the spectrum is basically like that: yz is equal to x dash z to the power l, where l is equal to 2, so it's 2. If we replace the value of x dash z here, we get the following: xz plus x of minus z which you can write in terms of omega as e to the power j omega plus x e to the power minus j omega. So option 3 is the correct answer. So let us move to the question 7. Okay, we consider the downsampler block diagram here, which is the input sequence xn is being downsampled with the downsampling factor of m to obtain output sequence yn. The question is, what is the maximum one-sided frequency of input xn such that yn is not aliased? Okay, so for that, let me write the let me first denote the input spectrum of xn as x e to the power j omega, and for yn, y e to the power j omega. Now from the previous question we have done, if we try to write y of j omega in terms of x of e to the power j omega, it will be like that: y to the power j omega is equal to let me write it in a little bit clear. It kind of looks messy. Okay, it would look like this. This term corresponds to amplitude scaling, this denote multiple copies of input spectrum. This you can see the stretching of frequency omega, and this is the shifted version. So okay, so for example, let me draw an arbitrary input spectrum of an input sequence which looks like this. We'll consider two cases. Two examples basically. Well, in first case, the input spectrum is limited to pi by m1. Now downsampling process leads to, I won't mention the copies, I will only focus on the one spectrum. You see there is a stretching of frequency. Now previously omega dash, which was pi by m1, okay, let me write it down a little bit clear way. First let me draw the spectrum and let me explain then. So this guy, you can see this results into stretching of frequency axis. So becomes like this. So due to stretching in frequency axis, omega dash pi by m in earlier omega scale frequency axis now becomes m time omega dash in new frequency scale. Okay, now you can see the input spectrum, which was earlier band limited to pi over m1, where m1 is some arbitrary integer. Now in the this new omega scale becomes stretched to pi m over m1, so its maximum frequency content becomes pi m over m1. Now we know that for discrete time spectrum the maximum frequency allowed is pi. If you go beyond pi, you run into the risk of aliasing. It's like aliasing is going to happen. So aliasing will happen if your maximum frequency, which is pi m over m1 here, is greater than pi. The moment you are crossing the threshold of pi, because of this frequency stretching property, that is the inevitable result of downsampling process. The moment your maximum frequency in discrete time spectrum is going to cross pi, you run into the risk of aliasing. So for not aliasing, what should be your condition? Your condition should be at your maximum frequency, even in stretched axis, which is pi m over m1 in stretched axis, should strictly less than pi to avoid aliasing. What does this condition leads to? M1 should have a value greater than M. So value of M1 should be strictly greater than M. Sorry, it should not be like that. It is equal to or greater than M to ensure aliasing is not going to happen. So what is the maximum one-sided frequency? Like if M1 is greater than equal to M, then max of pi over M1 for any arbitrary M1 is going to be pi over M, because it's inverse here. So M1 should take the least value to maximize this. What is the least value of M1 possible? M. So your maximum frequency is going to be pi by M. So your input sequence need to be strictly band limited to pi by M to ensure aliasing doesn't happen. So it corresponds to the second option. Actually, this is the reason precisely you use anti-aliasing filter. You use this low pass filter with cutoff frequency pi by M before performing a downsampling operation with a downsampling factor of M to ensure aliasing doesn't happen. So if you follow the lecture, pi by M is also the cutoff frequency of low pass filter used before downsampling. We also call it anti-aliasing filter. To avoid the problem of aliasing. Okay, let us move to the question number 8. It is not mentioned here. No. So you are given a sequence xn, which is 5 1 2 4 3 8 9 7 6 3. This denotes the 0th index. So what is yn? Okay, so instead of now moving into the manual way of doing it, like writing all the samples over and performing this tenuous operation over them and to find the output sequence out of that, let us try to proceed in a clever way. We can see there is two branch here, this one first, and then this is a, you can say this is advanced operation, this is a delay operation. So fine. So first let us denote the signal here as x2 of n, and the signal here as x1 of n. Now let us try to find what is x1 of n. x1 of n is obtained via first downsampling and then upsampling of xn. So let us write it quickly. Xn, first you downsample it with a factor of 2. That basically means it is going to keep only the even indices, that is 1, 4, 8, 7, 3. And then you perform this upsampling operation. Which basically introduces zeros between every pair of samples. So you can see this is x1 of n, of course. Now if you compare xn and x1 of n, you see x1 of n is nothing but we are keeping the even indexed samples of xn, and the odd indexed one we are turning it to 0. So it's like x1 of n is like multiplying xn with a comb sequence C2n. What is the property of comb sequence? If you remember it from the lecture, it is just C2n is going to be 1 for n even and 0 for n is equal to odd. When this index is 2, when this index is more than 2, it's like m here, so it becomes n for n multiple of m, and it becomes 0 otherwise. So for this particular case, comb sequence is something like this. Like 0, 1, 2, 3, like that. Minus 1, minus 2, minus 3, like that. Okay. So yeah, x1n we can denote it like that, xn multiplied by a comb sequence which is going to keep its even index samples intact and going to eliminate or bring down the odd index sample to 0. So let us see what we are getting here at this position. We are performing an advanced operation, so basically the output here is xn plus 1, and we are going to run an similar downsampling and upsampling procedure here. Okay. So let us do that. first. By the way, we denote the sample here as let me denote it as x double dash of n here. So when we advance this, let me solve it in a tedious way first, then we'll move the easier way. X n plus 1 is nothing but shift the sequence 1 to the left, is something like this. The 0th index is here now. So by repeating this procedure, I would write it for you now. We obtain x double dash of n as this. And you are performing this delay operation, that means x2 of n is nothing but x double dash of n minus 1. You shift it right to 1 unit. Okay. Now if you add x1 of n and x2 of n, I'm not writing it here because it will become messy. You will see that it will just turn into like this. It will become xn. Now instead of writing this sequence again and again and performing this shift and delay operations manually, can you do something smarter? Actually we can. You see, the advanced operation here results into xn plus 1, and these things, as we have seen, is equivalent to multiplying with the comp sequence like that. So basically when you reach here, this is nothing but x n plus 1 c2 n. Now when you pass through this delay block that corresponds to 1 unit of delay, you obtain x2 of n as n minus 1. Instead of writing all the sample values and calculating manually, see, I am just writing the sequence in a logical way. This in terms of xn comes out to be this c2 of n minus 1. So using the same principle here, we have obtained x1 as xn multiplied with comp sequence. Here we obtain x2n as xn multiplied with comp sequence, a shifted version of comp sequence. So when you sum them up, x1n plus x2 of n, we can see it like xn times c2 of n plus c2 of n minus 1. And this is the expression of c2n. Similarly, if we do some little bit of mathematical calculation, we'll see this will come out to be 1 for n is equal to odd and 0 for n is equal to even. So this is C2 of n. You shift C2 of n minus 1, delay it by 1 unit, you will get the following plot. It takes 0 value at even index and value 1 at odd index. So when you sum them both up, it just become xn, because com sequence now take value 1 at each point. Like this. This is at 0, 1, 2, 3, minus 1, minus 2, minus 3. So it is not eliminating any value of xn. It is just, you are just taking the product of xn with a sequence which takes value 1 at every index, so it comes out to be nothing but xn. So instead of doing this tedious calculation and shifting and delay and advanced operation, writing down comp, you can solve it in an efficient way as shown here, and you will see your result is the input sequence only. So yn is nothing but xn. Check which of the options matches, and it's the first one. Okay, let us move to the 9th question. Actually, you see, this asks that there are two branches given, both contain an upsampler block with upsampling factor of L and a downsampler block with a downsampling factor of M, and only difference between branch 1 and branch 2 is the blocks are reversed in the order, and the question is when are these two branches are going to be equivalent. So I have already performed the exercise for a practical case in earlier problem where I shown that reversing the order is not going to make change only when L and M are co-prime numbers. So this is true only when L and M are co-prime. Okay, if there is time left, I will come back to you and explain why it is so, although it's elaborately explained, beautifully explained in the lecture by professor himself. Let me move to the next question. Okay, we know xn is band limited to 20 kilohertz. What is the highest frequency component of next button? Okay, you perform a downsampling operation here, you perform upsampling and you obtain x bar n. So what is the maximum frequency component? So let us denote the intermediate one as yn. Let x to the power j omega, y to the power j omega, and x dash to the power j omega b dt spectrum of xn, yn, and x dash n respectively. Since the question is in terms of frequency, we will solve the problem in the spectral domain, and this will bring in some really important insights, what is really happening. So let me assume a arbitrary spectrum. This assumption doesn't harm our analysis. X E of j omega, let us say it is band limited to pi by a, where a is some integer. When you perform the downsampling operation, I won't take into account the shifted spectrum, only the main one that is centered around 0. You perform this downsampling operation, we have seen earlier, it leads to stretching of frequency axis. Omega is discrete time frequency, so this leads to a stretched spectrum. I am considering the ideal case where aliasing is not going to occur to avoid complications. So now it's band limited to pi m by a. Okay. Now you move to upsampling by a factor L, which results into contraction of frequency axis. Again, we know that upsampling introduces additional L-1 spectrums where L is the upsampling factor, but as of now I am again going to ignore the other spectral, like the copies of the spectrum. We are interested only in the fundamental one, the one around 0. Oh, sorry. So this contraction, so basically what is this change of scale from omega here, your omega prime becomes m times omega, and from here your scale omega double prime becomes omega prime over L, that is basically m times omega by L. So because of this contraction, now the signal is band limited to this. There should be no minus sign here. Let me remove that. Okay. So I have started with a very generalized case. I consider pi by a to be the maximum frequency, and we obtain the maximum frequency of the, okay, by the way, this is the spectrum of y to the power j omega, the intermediate sequence, and it is the spectrum of x dash of n. So you see the highest frequency component of x dash of n found to be pi m by l a. So now according to the question, pi by a corresponds to 20 kilohertz. See, there is not equal to, it's not equivalence. The representations are different. It's in hertz, where it's in radian. So yeah, okay, but there is definitely equivalence. So what if pi by a corresponds to 20 kilohertz? What should pi m by l a corresponds to? You can see there is clearly this is a multiplication by scalar on both sides. What is the scalar amount? M by L times 20 kilohertz. You put the values in the question. M is equal to 5, L is equal to 6. So your maximum frequency component of x dash n is going to be 100 over 6 kilohertz, which if you do the fractional operation comes out to be 16.67 kilohertz. Actually the option here should be 16.67, not 16. So the maximum highest frequency component of x dash n is 16.67 kilohertz. Let us move to the next question, which is again a statement. So during interpolation, we know to remove the image, the first statement is during interpolation, to remove the images created by the upsampler, a low pass filter is required. Yes, correct, but yes, that is after the upsampling process, because if your spectrum, let's say input spectrum from minus pi to pi, you perform a upsampling process by L, this leads to additional L minus, first of all your each bandwidth of each spectrum is contracted, it becomes pi by L to pi by L, and also additional L minus 1 copies of spectrum are introduced. This corresponds to 2 pi over L, this corresponds to 3 pi over L. So to perform interpolation, you need to have a low pass filter here after upsampling process to filter out this copy only, to remove the additional images of the spectrum. So this statement is correct. Next we move to the during decimation, to avoid aliasing, a low pass filter is required before the downsampler. It's correct. Basically, let me write it here. For upsampling process, L, it followed by a low pass filter with cutoff frequency pi by L to remove the additional images of the spectrum. For decimation process, by the way, you need a low pass filter before to keep the frequency of the input sequence in check, or to make it band limited. Here it should be pi by m if you are going to perform downsample by a factor of m. This is why, because you need to avoid aliasing. So let's say your input signal is band limited to something like that, pi over m1. So this low pass filter is going to make it band limited to pi by m. So that when you perform the downsampling process, as a inevitable result, the frequency axis got stretched. Therefore your spectrum become limited to minus pi to pi as a result of this stretching of frequency axis. If it doesn't do that, if you do not use low pass filter, it is not going to cut off the frequency component beyond this point, which will inevitably lead to aliasing. So during decimation process, to avoid aliasing, a low pass filter is required before the downsampler to make the input sequence band limited to pi by m. So both the statements are correct. We will proceed to the third statement, that there is never loss of information in downsampling. That is not correct. Downsampling, when you perform downsampling, you always run into the risk of loss of information. So the correct answer is the fourth, both A and B. Let us move to question 12. So here are some frequencies given. Xn is equal to cos 0.45 pi n plus cos 0.4 pi n. So what is the maximum frequency of the signal? F max is max of 0.45 pi or 0.4 pi, 0.45 pi, that is 9 pi by 20. Let me write down the frequency component of the individual signals first, so that later we can see, based on the maximum frequency component of xn, in which of the cases the aliasing is going to occur. And this is for the first signal, and for second signal, your xn is going to be cos of 0.45 pi n times cos of 0.4 pi n. This is again cos of 0.85 pi n plus cos of 0.05 pi n. So you can see the f max is max of 0.85 pi, 0.05 pi, 0.85 pi, which is 17 pi by 20. Now first try to find in which of the cases aliasing is going to occur. Now when it passes through the upsampler, if it's a max let me write it for the generalized case. Let max frequency of xn is omega max. So after upsampling, the frequency axis is contracted, your spectrum bandwidth contracted, I mean for individual copies, and it becomes max frequency is omega max by L. Now after downsampling by a factor of m, the frequency axis is stretched, therefore your maximum frequency increases. Your maximum frequency omega dash max is omega double dash max becomes m times omega dash max, which in terms of the original frequency of original sequence xn can be written as m by L omega max. Now to avoid aliasing, max frequency m by L omega max cannot cross pi. The point has been stressed in lectures repeatedly again and again, and I have also mentioned in context of previous problems that to avoid aliasing, your maximum frequency cannot be more than pi. This is a fundamental constraint. So we put the value of m and L. M is equal to 4, L is equal to 3. So it's like 4 by 3 mega max less than pi, which if we want to write in terms of the maximum frequency component of original sequence xn, turns out to be it should be less than 3 pi by 4. Now let us check for fast signal. is 9 pi by 20 less than 3 pi by 4. Correct. So in first signal, aliasing on talker. For second signal, which is 17 pi by 20, is it less than 3 pi by 4? No, absolutely not. It is greater than that. So second signal aliasing will occur. So only case of first signal aliasing won't occur. So our answer is option A. Let me take a 2-minute breaks here. I'll be back. Okay, let us move to the question number 13. You see, a continuous time signal is a sample or the sampling rate of t, then it's being upsampled, went through a filter, then we multiply it with e to the power j pi n, and that results into a sequence yn, then you get back the output signal, continuous time signal YCT. You are supposed to find the spectrum of YC of j omega. Now it is the input spectrum of XCT is given in analog frequency domain. Let us draw the spectrums one by one. So this should be the discrete time spectrum of Xn. Xn we denote it as x to the power j omega. For Bn, v to the power j omega. For Wn, w to the power j omega. For Yn we denote it as y to the power j omega. So let's start. So you can see the spectrum of x e to the power j omega is given as minus pi to pi. This we obtain from this. This is denoted as sigma m. So continuous time to discrete time frequency relation sigma m times t is equal to omega m. We obtain omega m as pi. Therefore it spans from minus pi to pi. After performing this upsampling operation, it results into contraction of frequency axis. So v of e to the power j omega, it becomes pi by L to minus pi by L. There are additional copies also. We assume a low pass filter, it passes through a low pass filter. Oh, sorry, there is no assumption. Let me highlight it. Okay, this is pi by L, this is minus pi by L. There are additional spectrum here. L minus 1 is 2 pi by L, that is 3 pi by L. L minus 1 additional spectrum. You multiply with h to the power j omega with the cutoff frequency pi over L. So after passing through this low pass filter, the resulting spectrum denoted as y to the power j omega, it only gives this spectrum and remove the additional ones, additional images. So omega is band limit, w is band limited from minus pi by L to pi by L. Now you multiply with minus 1 to the power n e to the power minus j pi n. By the way, there are additional copies here at 2 pi discrete domain, 2 pi here also at minus 2 pi. So let us move to the next slide. Okay, so we see that there is a multiplication with the term e to the power j pi n. This multiplication corresponds to advance by pi in discrete time frequency domain. This is discrete time Fourier transform property. Like if xn has this thing x e to the power j omega, then if you multiply xn with e to the power j pi n, it corresponds to a shift of pi on left, basically advanced by pi in discrete frequency domain. So let me go back to the previous picture. So the yn is going to be something like that. Sorry, the spectrum of yn denoted as y to the power j omega. Your copies are now shifted by pi, so that the one copy at 2 pi is now become shifted to pi, and this one is shifted to minus pi. And this is pi minus pi by L. This is pi plus pi by L. Now we perform the sampling. Rate t dash of s at t by L, so that the spectrum is not getting distorted. So as we see, when you move to discrete time domain to continuous time domain, yc of j omega, you see any components outside pi, you need to essentially remove it. So sorry, just a moment, let me use the pen here. Yeah, so if we denote it is band limited to omega s, it is band limited to omega s, so omega s t dash s should be equal to pi. Therefore your omega s should be pi L over t, pi L over t minus pi L over t. So this mapped into this. This is in analog frequency domain, this is in discrete frequency. Sorry, I just made it just the opposite. This is in discrete frequency domain and this is in continuous frequency domain. So the spectrum of the output signal yct in the continuous time domain is going to look like this. Therefore your answer is this is moved by left. this one. This question says that linear filter has impulse response Hn such that the Hn has two properties. Hn is equal to h of minus n, so it's symmetric, and Hn is equal to 0 for norm of absolute value of n then RL minus 1. So you can see that let us say it's a interpolation filter, so Hn will look something. Let's consider a practical interpolation filter, a triangular one. So it will look like this, something like this. I'm like drawing arbitrary. That assumption won't harm us. This is minus RL minus 1, this is RL minus 1. So clearly this is not causal, because it has presence. Hn has non-zero values at negative indexes. So to make it causal, we have to insert the delay. Insertion of delay corresponds to shifting of sequence to right. Now if you see, it has presence up to minus RL minus 1th index, non-zero values. So you have to introduce a delay of RL minus 1 unit to make it causal. We have to introduce RL minus 1 unit delay to make the system causal. Therefore the third option is correct. So let us move to question number 15. Your continuous time signal xct is sampled at sampling rate of t to obtain discrete time signal xn, after which it passes through a upsampler block, the upsampling factor of L, then it passes through this filter, then we downsample it and we obtain yn. Fine. So let us move. So where from we start? Let us denote the sequence here after upsampling as x dash of n. The question I have written here is wrong. It should be pi over L, not pi L, and this is pi over t, not pi t. Just a minute. Okay, fine. So x dash of n is upsampled version of xn. So x dash of n we can write as x n by l, which also can be written as xt of n t over l. Now we see that h of j omega, the frequency response of the filter, is given as e to the power minus j omega for this region only, pi over l. So if you see from the properties of Fourier transform, it's like an inverse Fourier transform. If x of n is going to have a dtft given by to the power j omega, then x of n minus n naught is going to have this property. Therefore we have to, this is actually Fourier transform, we need to take inverse Fourier transform, that is we denote the let x bar of to the j omega ft of x dash of n, let us denote it as x double dash of n here, so, and x double dash of the power j omega x double dash of n. So you can see x double dash of to the power j omega is equal to x dash of the power j omega times h to the power j omega j omega to the power j omega. From the substitute the expression of h to the power j omega from here. Therefore x double dash of n, taking inverse Fourier transform, we can write in terms of x dash of n as minus 1. Okay, and this in terms of xn can be written like this, n over l minus 1. Now see that when we downsample x double dash of n, we pass it through a downsampling block, we get yn, and that results into many things. Prominently of them is like this: you have amplitude scaling, you have multiple copies, of your input spectrum, your frequency axis, there is a stretching of frequency axis, and there is this frequency shifts. So okay, so when we transmit all into this, by the way, downsampling here by L means your sampling rate T dash of S is LT. So Yn you are going to get as x double dash f ln with a amplitude factor. Just a minute, let me write it in a clear way, it becomes messy here. Okay, okay. Now remember, your sampling rate is t dash of s is L over t, so it becomes xc nlt over L minus t over L, which results into this relation. So option 1 is the correct one. Now we have solved kind of similar problem before. So h0 of z corresponds to no delay, as you can see here. Is it should be 1 of z, it should be h2 of z. h1 of z corresponds to delay by 1 unit, and it corresponds to delay by 2 unit. So if we write it down, y0 of n is equal to xn multiplied by just a minute. Okay, you can write this as product of consequence y1 of n is x n minus 1, this, and y2 of n, you can see it's xn divided by 2 unit multiplied the consequence. With a slightly change of index, we can write it as xn c3 and plus 1, and this one as xn C3 n plus 2. So when we sum them up, y2 of n xn c3 of n plus c3 of n plus 1 plus c3 of n plus 2, and this corresponds to 1 for all n. So we can recover y0n being upsampled by a factor of 3, sample factor of 3, upsampled by a factor of 3. Sorry, I was just made a quite big mistake in understanding. It should be upsample version of y0n. Okay, let me put it in the correct way. When you upsample the signals y0 n, y1 n and y2 n with the upsampling factor of 3, then you get these sequences. And plus y1 n by 3 plus y2 n by 3. We can recover xn in this way. It should not be equal to, it should be the result of this. Okay. I guess there is some logical error in this question. I will correct it and upload it later. Okay, so let us move to the question 18. It says that this filter acts as both interpolation and anti-aliasing filter. What should be the single-sided bandwidth of it? Okay, so again we assume with arbitrary spectrum of xn, xn as x e to the power j omega as pi by a minus pi by a. After upsampling, you know there is a contraction of frequency axis. So new axis become contracted, and your similarly the bandwidth of your one copy of spectrum reduces proportionally. It becomes pi over LA. It's pi over LA. I'm not considering these additional spectrums here because I assume this filter H is, which I denote with some different color. This is low pass filter. low pass filter is going to remove the frequency component beyond this point, so that this additional L-1 copies are gone. Next, when you perform this downsampling operation, this leads to stretching of frequency axis, so it becomes stretched. It becomes pi m by L A, pi m by L A by the power j omega. So to avoid aliasing from down sampler block, input signal must be band limited to pi by m, and at interpolation to remove additional copies of spectrum, cutoff frequency must be pi by L. We need to satisfy both conditions. Okay. So let us consider if pi by L becomes greater than pi by m. Problem of aliasing. So answer is you should take minimum of both pi by L or pi by m. In that case, you will avoid the risk of aliasing, because if pi by L is greater than pi by m, there will be problem of aliasing. So pi by L is certainly not going to be a solution. If pi by L is less than pi by m, that is also a valid solution, but this summation is not a solution. Neither this is going to be solution, because it is going to distort the spectrum after upsampling, because it is less than pi by L. You cannot allow it to be less than pi by L. Now if you choose maximum of pi by L and pi by m, you run into the risk of having this, which eventually lead to aliasing. So only this option cancel out, only the third option stands for, because here you see L is equal to 3, so it's minimum of pi by 3 and pi by 4. So option 3 is the correct one. And this is a similar question only, that in which of the case following cases aliasing is not going to occur. for aliasing not to occur. In case of first case, your input should be xn should be band limited to pi by m, that is pi by 3. This is sufficient condition. So let us check one by one. For xn cos 0.3 pi n, what is the maximum frequency? 0.3 pi, 3 pi by 10 less than pi by 3. Satisfy, therefore it satisfies the condition for not aliasing, because its maximum frequency is less than pi by 3. Maximum allowable frequency is pi by 3. For second signal, xn is equal to cos 0.5 pi n plus cos of 0.4 pi n. The max is going to be max of 0.5 pi and 0.4 pi. 0.5 pi, which is pi by 2, which is greater than pi by 3. Therefore aliasing will occur in this case. For third case, this cos 0.4 pi cos 0.5 pi n. For this, your maximum frequency, I am not going to calculate it, you can do it yourself. It comes out to be max of 0.9 pi, 0.1 pi, which is 9 pi by 10, which is definitely greater than pi by 3. Hence aliasing will occur. This is also not the correct option. The fourth one is cos 0.4 pi n, where the only frequency component is 0.4 pi, which is 2 pi by 5, is greater than pi by 3 again. So in this case also you would run into the problem of aliasing. So first one is the correct option. So with this I end the session for today. We'll next meet next Tuesday for our 4th week session. Thank you. And I'll also upload these slides in the folder where you can anytime access the solutions. And I will also provide I will try to provide the correct explanation for problem 15 in the slides. You can refer to it later. Thank you all.